My name is Brandon Burdett, and welcome to my Physics Lab 6 Magnetic Molasses. As a little introduction, the experiment is dropping a bar magnet through a tube which is surrounded by aluminum foil. The coding in this lab is creating a computational model of a magnet falling through the tube, which simulates this tube which is surrounded with the aluminum foil. And the purpose of this is to examine the effects of magnetic forces. Here is a preview of the results of how fast it was falling through, with the amount of time it took to fall being 1.134 seconds, which is important to keep in mind. In this lab, the system is the bar magnet, and the surroundings include both the earth, aluminum foil, and the tube. A couple of the key principles in this lab are the force of gravity, where F equals mass times the gravity constant, and also knowing the equation for magnetic field, which is seen on the right side of the screen. Some other key principles in this lab include the magnetic flux equation on the left, and then also both the velocity update formula and the position update formula, which are both seen on the right. So within this experiment, we were tasked with surrounding a cardboard tube with aluminum foil, dropping a bar magnet and letting it fall through the tube, and then recording the time it takes for this magnet to fall, and doing this 5 times. Now on the left is the video of my group doing this, but I'm just going to show you as a picture because the video quality is very bad. You can't even see the magnet, but that's kind of what the setup looks like. And then on the right side of the screen here, you can see the amount of time it took for the magnet to fall with each attempt, and the average time being 1.26 seconds. Now I will get into my glow script model. Some of the initial conditions include a couple constants that are always the same, and then also the resistivity of aluminum. And then in this middle section, it's the geometry of the tube, including how long it is, how wide it is, and then also the foil surrounding it. And then at the bottom, there's both the mass and the magnetic dipole moment, which we used in a previous lab, or found in a previous lab. Now on the top is the formula for a function which is creating a magnetic field of the bar magnet, and then here at the bottom is another function which is calculating the magnetic flux. Now some more of the calculations are the gravitational force, and then also the current of the ring, which is found by using the flux, and then also going through and finding the using that function found on the last slide for the flux, and then using the current of the ring to find the magnitude of the force on the ring. And then once you get this force, you add it to the force of gravity, and that gets the net force. And using this net force, we can go back to physics 1 and then do the velocity update formula, and then we can use that for the position update formula. Here's what my coding output looked like with the magnet falling down, and then there's the graph on the right. Now comparing these two different experiment and computational models, in the experiment our average fall time was 1.26 seconds, and then in the glow script model it was 1.134 seconds, which these are very similar, and it proves that everything was correct and going as it should. And then there's a little bit of dissonance, which I'll get into soon. Some of the reasons for the error could just be an imprecise stopwatch or imprecise measurements, which we used to put into the tube geometry, and then also just air resistance and friction with the tube wall while the real magnet was falling. Now, if the resistivity of the conductor were very close to 0, according to Ohm's law, the current would have to go up very high, and this high current leads to a stronger magnetic field, and this ultimately would cause the magnet to fall slower. Now, if holes were to be cut into the tube, the ring current would be disrupted, and there would also be some asymmetries most likely, and these asymmetries could create a torque, which would then make the magnet spin while falling. Thank you for listening to my lab.